comparison between all the stuff we're doing with angular momentum and all the stuff we did with regular momentum. So let's put the angular part on here. Momentum. And we have regular momentum. So, right, so regular momentum, P is mv in the non-relativistic setting. Here we have L is R cross P. The units are different. And we have force is dp dt. And we have torque is dl dt. So that's the angular momentum, and these are also vectors. This is torque. So force turns into torque. And then we talk about energy, so kinetic energy. Is the center of mass kinetic energy plus the rotational kinetic energy, which we could also write as 1/2 I omega squared. And this is also the spin or rotational kinetic energy, and that would be with respect to the center of mass. Here we had K is equal to the same thing, 1/2 m in the center of mass squared plus the sum of 1/2 m. So these are all the particles in the system, v minus the center of mass squared. So in the regular momentum setting, we showed that you could always write in a system, you could always describe the kinetic energy as the sum of the total mass and center of mass velocity plus a sum of the velocities and the velocities with respect to the center of mass. And this, when we're talking about vibrational degrees of freedom for like a two mass thing, you could write it as the reduced mass times the difference between the two. This turned into that. So it turned into this thing that depends on the moment of inertia. So the radial, so when you have rotation, the velocities depend on the radius from the center. And this took that into account, because the moment of inertia is the integral of the mass distribution times the radius squared from the rotation axis. So that was the analogy. And then there's one more thing that we talked about. So you can always take a velocity and describe it with respect to the center of mass. So the thing that I lectured on last time is I showed that for a system, you could always write the total angular momentum as the angular momentum of the center of mass plus a spin term, where this was the R cross M center of mass, V center of mass, because that's R plus P, and this is I omega. So the L spin I omega, and likewise when we write the torque, it's the time derivative of this. So the moment of inertia is fixed, and the angle. So this is a vector. So this is also a vector. And so this omega, we then gave it an axis, a spin axis. And so when you take this derivative, you can describe, so if the moment of inertia is not varying, then you can describe the time derivative in terms of an angle change and a rate of angle change. So if the axis is not changing, then this turns into I omega dot, or so which is I it's the angular acceleration. And when you talk about things like precessing tops, then the direction is changing, and so you need to take that into account. So this is if direction or axis is fixed. Okay, so that's kind of what we did. You can kind of see the analogy between force and torque, although the units are different. So we're going to talk about units. We have a little bit before we get to that. Okay, so last time I gave this example of a pulley with a string, and there was like a roll without slip condition that let us solve for things like the angular acceleration in that sense. So I'm going to do another example now. So the example I want to talk about now is the compound pendulum. And it's relevant for an additional reason that for the online people, the fourth lab is actually on a compound pendulum. So let me tell you what a compound pendulum is. So you have some pivot point. So normally a pendulum, you have some string or a rod or something, and then you have a mass hanging at the end. So compound pendulum is just some arbitrary object that you put a pivot point on, and then you let it swing back and forth. So it's a rigid body that's now allowed to swing. So this is the compound. So one of the things that's nice about the compound pendulum is that what I'm going to show is if you measure the period, it's not just sensitive to the length. So the main thing that, so before I wrote down the angular momentum is the center of mass angular momentum plus I omega. You can do that here, but also describe things with respect to the pivot point. So so there's a, let me guess where the center of mass is. Here's the center of mass. So there's a particular distance that's important, which is the distance to the center of mass. And the period, not surprisingly, the period of the oscillation will depend on that distance. But the period of oscillation will also depend on the mass distribution. And so not surprisingly, it's going to depend on, so if it's really compact, then it will be just the same as a regular pendulum. But, stuff up here is not moving, so it's not part of the pendulum motion. So the period is sensitive to that. So it lets you get a measurement that's sensitive to the mass distribution. And that's sometimes really useful. So what if you don't know what's in it? And that's what, that's the question that I've asked on the fourth lab for the online labs. What can you say about the internal mass distribution for measuring this? So this is like, if you can't see inside and you want to learn about it, measuring the moment of inertia can give you some information. And that's used. So if you can come up with a constraint on the moment of inertia of a planet, for example, it lets you put constraints on the mass distribution inside the planet. You can't see inside the planet, but models for like how much rock versus ice or something, or what the equation of state is in Jupiter, which seems to be a hot topic right now because of the Juno mission. Those quantities are set. So the mass model is not just is dependent upon the density distribution, and the density distribution is dependent on sensitive to the evolution and the phase of the constituents. So it's actually an interesting constraint. recently, actually, so this is cool. So I don't know if any of you guys were paying attention to the Osiris-Rex mission sample return exercise they did a couple days ago. But they almost landed and they pushed this thing into the surface of the asteroid Beidou. And now these pictures showing the surface actually like crunching and stuff flying off. And they filled their bucket, which is their sample return bucket, and then they took off. They wanted to know not just how much mass they collected, but they also wanted to have a feeling of how it was distributed inside the sample return container. So they spun it. So it gave them a measurement of the moment of inertia. So this is actually this idea that when you spin something, it's sensitive to the mass distribution was used recently on the Osiris-Rex mission to try and guess at where the how much sample mass and where the mass was inside it. Okay, so it's useful. And I've used this in the lab actually too. So in the lab, we built this complicated pendulum apparatus to reproducibly launch projectiles. And the main reason is so that we could get projectile launched the same way more than once. So just let this thing swing, hits a bar, and then off comes the projectile, and you can adjust the angle by where the bar is, and you can adjust the velocity by how high you let the pendulum drop. But we had it wasn't just a string with a weight, it had a rod, a stiff rod. And it's like, so I could have added up all the pieces of mass and tried to compute the moment of inertia in order to figure out what the velocity was going to be. But instead, I just measured the oscillation period, and that gave me the same information. So you can, I actually found this was useful, experimentally useful. Okay, so let's work on this problem. So we have just like we did with the pendulum, we can put an angle theta here. And then mg. So the total mass of this blob thing, we'll call m. And mg is the force of gravity. And we can think of that as applied on the center of mass. So, I mean, we could think about is that really true? Like, should we integrate it up? But if you integrate it up, because the gravitational acceleration is a constant, it's equivalent to just applying it at the center of mass. So, and another way to know that is when the force is the gradient of the potential energy, and the potential energy is only dependent upon the center of mass for gravitational acceleration force. So that's another way you know that you can just apply this at the center of mass. So the component, so when I take, now if I want to compute the torque on this thing, I take R cross F, and F is this thing, but I don't care about the component that's radial because the body is rigid. So I only need the tangential component, and that depends on theta. So the torque will depend on mg, so that's the force, times R, so it's R cross F, R center mass. And then there's this angle term, sine theta, and then because it's that way, we'll give it a minus sign. And we set this equal to I theta double dot. So what's this? This is, so L is I omega, which is I theta dot, and torque is dl dt is equal to I theta double dot. So that's what I've done here. And I is with respect to the pivot point. So it's the moment of inertia about this rotation axis. So just trying to be careful about where I'm doing I. Okay, so in any case, this, so let's be specific about that. I about the pivot. So that's the rotation axis. I is the moment of inertia. Okay, so this thing is hard to solve. Let me turn this off. Okay, so, this thing, is easy to solve with this theta, sine theta turns into theta. So we're gonna take a small angle approximation. So a small angle approximation, just like we did for the pendulum. So that means we have minus mg r center mass theta is equal to I theta double dot. And yeah, so let's move this onto the other side. The r center mass over I minus sine theta double dot. And that's the same equation of motion we had for a harmonic oscillator. Oh yeah, we have a question.
Yeah, so would you want to add in the negative, or would you just, because your negative is going to pop out with your sign, if you put in, like, if your zero angle is like in line with your radius, would you just want to put in a negative angle and then?
Oh yeah, so if you want the force to be this way, and if it's on the other side, it's in the opposite direction. So the sine theta has that, gives you the right sign, so it's always in the direction towards small theta.
Gotcha, okay.
Yeah, and that's the same that we had for our harmonic oscillator when we had m x double dot is k minus kx. So it's the same type of thing. Yeah. So yeah, I think so. There's nothing wrong. If it had been a cosine, yeah, because cosine doesn't matter what the sine cosine of theta is equal to cosine of minus theta, but sine minus theta is equal to minus sine theta. You could just take the sine out because it flips. Okay, so and actually looking at this analogy, if you guys are used to looking at that, you can automatically, here we know omega is the square root of k over m. And so looking at this equation, the moment of inertia kind of acts like the mass, and this acts like the spring constant, actually. So you can immediately write down the frequency of oscillation is this. So instead of k over m, it's mg r center mass over I. And so this works great for small oscillations. But often with a compound pendulum, that's what you're using. So I worried about that in the lab. Pendulum, this small angle approximation is really good as long as it's a small angle. And it's not as good when the angle gets bigger. So, so if you have a really compact object and you're using it like the compound pendulum, which is exactly what we're doing in the lab number 4 for the online lab, then the small angle approximation is not actually all that good. And then what happens is the period. So the period, remember, is 2 pi over omega. What happens is the period gets longer if you have a bigger amplitude in the oscillation. So if you start off the period very close to the, near. So think about a pendulum. If I pull it very slightly off vertical and let it go, it will oscillate back and forth, and that's a small amplitude. But if I pull it much further, then the amplitude of oscillation is bigger, and the period would be longer. This is independent of the amplitude, so this is really only valid for small angles. And that's true for both the pendulum and the compound pendulum. But it's maybe more of a problem for a compound pendulum because you might be swinging in at larger angles. So that's kind of the point that I wanted to make. So this once you put this in here, then you get the period. And if you measure the period by, like, say, measuring how long it takes to reach its peaks, then you get a constraint on the moment of inertia. And the moment of inertia then has it's the integral of the mass distribution times r squared. And so it's sensitive to how the mass is distributed inside. So for the online lab, you guys will notice that you can say, well, what do I expect from the moment of inertia of a same size thing that's uniform density? And you can compare the two and decide is it consistent with it or not. And it's actually not. So you do get some information that the mass distribution inside is significantly different than a uniform density thing. So that's in the online lab, but presumably with the baby mission, they got some information on how for the OSIRIS-REx sample return and spinning thing, they got some information about how the mass inside was distributed. It's not a lot of information, but it's some information. Okay, so that's a compound pendulum. So, where are we headed? What I'm going to do is look at find the right units before I go on to another example. I don't know where it is, but we'll just talk about it. What's that? Bring it down. Actually, so it's convenient. This particular graph is, this particular blackboard is convenient. So, start with, momentum, mass times distance divided by time. With angular momentum, there's an extra distance in it. So, this is mass, distance over time. And we have mass, distance squared over time. So there's this extra distance in here because of the r. And then force, you've got mass times acceleration. With torque, you've got mass times acceleration times another distance. And so torque, the units, mass times acceleration, which is distance over time squared times distance squared. This is actually the same as mass velocity squared. So torque is actually in units of energy, it's the same units of energy. So that's maybe, I don't know, kind of something to keep in mind. Sometimes, I find I check the units a lot to make sure I've got the right answer. And actually, if you look over there, the frequency, omega is mg r over I. So we have a mass times an acceleration times the distance divided by a mass distance squared. And that altogether, all the units of distance and mass cancel out, leaving just 1 over t. 1 over t squared inside the square root. So you can kind of see how that works. But so keeping in mind the units are mr squared. So if you just remember that, it's easy to check. Other than that, everything just kind of follows for remembering that torque is r cross f. I should have put here. So if you remember that, you remember this, and you remember I omega, then it's pretty easy to remember the units for things. Okay, so let's move on and talk about conservation. So let's remind ourselves, we showed that momentum is conserved when you have a system and all the forces are equal opposite inside the system. So you have a system of a bunch of masses or something, and then there are interactions between the masses. if all of those interactions are internal in the sense that they apply to each other and they're all applied as equal and opposite forces, then the total momentum is conserved. So we showed that. And so now what we're going to do is say, well, what do we need? What gives us conservation of angular momentum? So we're going to follow the same analogy and show what happens then. So, let's find some more time. So let's talk about conservation. So, we have dp dt is f, and now if we have a bunch of particles, so if we have point masses with positions xi, and they're interacting with forces Fij, then the force on particle I from particle j is that. But so this is exactly what we did when we showed conservation momentum. We said the total momentum is the sum over all particles, and then we looked at the change in momentum over a little length of time. And then because Fij is minus Fji, for each particle that we had a change in momentum, another particle had the opposite change in momentum, and so the total momentum was conserved. So that's how we actually showed that. So now we're going to do the same thing, but writing L is equal to R cross P. So the total angular momentum is, so let me rewrite that with a sum now. It doesn't matter where we're picking the origin for the R. Xi cross Pi, and these are for each particle. So, so this we can substitute in there. Xi is the positions cross the sum over all j not equal I, because we're going to sum over all. So this is the momentum on particle I. F I j. Okay, so I've just substituted this in there. So so let's look at a single pair. Ij. So we have xi cross Fij plus xj cross Fji. And so this is a single pair of terms in this. So if we're summing over all particles I and all possible interaction terms, so you get n squared terms in here, except that we ignore the ones, we don't let particles exert force on itself. So it's n squared terms minus n, because the I terms are not in there. So let's rewrite this, because so this is the opposite sign. So I can put this like this with a minus sign. So this is xi minus xj times Fij. So this is so what does this look like if I have particle mi, particle mj, vector here is xj minus xi. So if the force, and there's a cross product here, cross. So if the force is along this direction, like it's pointed between the particles, then this is parallel to that, and it equals 0. Parallel to xj minus xi, then xi minus xj plus fij is 0. So that means we can take the sum and write it out as pairs of terms that all give 0. And so if this condition is satisfied, then L is not going to change in the sum. And actually, what did I do? I didn't mean F, I meant dl dt. Let's fix this. ddt, and I put that there. And so dl dt. So there was some small step here that I made a mistake on. Because this I put there to give that. So dl dt is 0 and L is conserved. I didn't want to prove that angular momentum was 0. That would have been bad. I wanted to prove that dl dt is 0 so that L is conserved. So that is a condition, right? The condition is that all forces have to be applied between points radially. And that's certainly true for gravity, and it's true for electrostatic forces. And if you write a numerical code where you apply all forces between points, it will automatically conserve angular momentum. And if you don't, if your code does an approximation where you don't do that, then your code will not conserve angular momentum. And so this is actually interesting that many codes, like SVH codes, have small problems with angular momentum conservation. They may conserve momentum, but they may not conserve angular momentum exactly. And that has to do with these slight offsets in the force. If you're averaging, for example, over nearby particles, then you might not exactly satisfy this. So I've noticed that, and actually, and since I've been doing numerical spin dynamic simulations, I've been very careful to make sure that all the forces are applied between points in the radial direction. And that's let me actually do some spin dynamics problems that other people hadn't been able to do. So involving deformation, tidal deformation. So yeah, it's not very complicated, but nevertheless, many numerical approximations do not do this carefully. Okay, good. So let's shift to some, since we have demonstrations, we can think about demonstrations now. So let's switch over here and play with some toys. Okay, yeah. So I'd like to bring this a little bit closer. That looks good. Okay, so check that you can see it. Yeah. Okay. So first demonstration, we have this wheel thing here, and you can roll up the string on it, so it's like a yo-yo, really. And the wheel's pretty heavy; it's this big metal thing. And when it gets down to the bottom, it's spinning really fast. So let's just look and see what happens. So it acts like a yo-yo, it comes right back up. So because it's spinning at the bottom, it doesn't just stop. So it has enough, not 100% rotational energy because it's not very well balanced, but it's not too bad. It goes for a while. So this kind of illustrates that you don't just get rid of rotational energy that easily necessarily. So it's not quite conservation of angular momentum, it's an energy thing. So the experiment we have with an ice skater, you guys all know if you spin and then you bring your hands in, you start to spin faster, and then you go out and slow and then fast. This is the whole how to do this and ice skaters and things spin faster. So this is maybe not surprising. So if angular momentum is conserved, if I make I bigger, and if this is conserved, then if I is bigger than omega is smaller, and if I is smaller than omega is bigger, when I bring my hands in, I'm making I smaller, and so omega has to go up, so the spin speeds up. So that's kind of what that shows. So what else? Oh, other things. So collisions, right? So when you hit something, here's another setting. If I have something round and I throw off mass, then just like we had with thrust, where you can change momentum by ejecting mass with a rocket, with angular momentum, if you toss out mass with a lever arm, then you can, spin something up. So if I take this and then I toss it that way, then I start to spin. So like in space, you could do this. If you're a spacecraft, you need to eject mass at an angle in order to start to rotate or to stop rotations. And likewise, if somebody throws that at you, if you catch it off center, you can start to spin. So those are, that's maybe an example of torque, possibly. So then what else do we want to talk about? We want to talk about stability, actually. So, yeah, so let's put up the stability demonstration. So let me remember how to do this. So this is a perception, actually, let's do the stability one. So this, so I practice doing this. The way this thing is set up is, so I started it spinning and it's staying up, right? But if I just do this and let it drop, it falls over instantly. So this is an example of how a gyroscope helps you stabilize something. And so you know this qualitatively when you are on a bicycle, that the faster you go, the less likely you are to just tip over. So, so I thought before we do more of these experiments, let's talk a little bit about stability. Let's take this up. So before we talk about precession, to the other video thing. Good. So before I talk about precession and Keplerian angular momentum in the Keplerian orbits, we'll talk about stability. So stability. And mainly because of spin. So, I don't know, so I was trying to think of examples for stability and to try and explain them, not just to say qualitatively, but just actually to think about them. So, a nice classic example is a tightrope. So you know this, like, this is a circus trick, right, where people get on a tightrope and their feet are like this on the rope, but then they either put out their arms really long, really as far as they can to balance, or they have this pole, and they use the pole to balance. So, so here's the rope, and then they have some guy with feet standing, and then he's holding on to a rope, holding on, either he has his hands out or he's holding on to some kind of a pole. So, why is it that the having the pole helps him stay up? And so, you know, he's trying to increase the moment of inertia, right? Because he's trying to put mass far away from himself, either with his hands or the pole. So you know it's got to be related to the moment of inertia. But the picture that's helpful, so you put his feet here, and his feet's on the rope. So this is the pivot point. Here's the mass. So let's assume that he's starting to fall. So there's some angle theta, and here's mg down. The question is, how fast did he fall? So, so we can think about that. Just like our compound pendulum problem, the torque is mg, so I need an h. So let's say the distance from his center of mass to his feet, which is the pivot point, is h. So it's mdh times theta is the torque in this direction. So when we had the compound pendulum, the torque was that way. This is upside down. So the torque is in the opposite direction. So instead of like your question, where the torque is always in the restoring direction, in this case, it's actually the opposite way. It's actually causing him to fall. It's an unstable setting. Just like the inverted pendulum, it's going to fall over. So, and this is equal to I theta double dot. So I is the moment of inertia of his mass. So he prevents falling by redistributing the mass. So I is not going to be constant. So there's a control problem on redistributing the mass with changing I. But so this now, the solution is not a sinusoidal solution. It's an exponentially growing solution. It has the same time constant though. So instead of having solutions like theta is theta 0 sine omega t, we have theta 0 is equal to e to the omega t. And it's growing. And omega is the same thing. It's going to be this mgh over pi. So just, I know we don't have the compound pendulum example up. So if I is large, omega is small, and it takes a really long time for him to fall over. And if I is big, then omega is small, and he falls over really fast. And this exponential thing drops, grows really quickly. So the tightrope example kind of shows you it's actually a control problem. So if you're taking engineering classes, you'll discuss how fast do I need to adjust something in order to achieve stability. And I'm not actually solving a control problem here. Instead, what we're saying is the time scale for things to happen depends on this. And so I'm probably going to have to control it faster than that. So I'm not telling you how much I need to move things, but I'm telling you how fast I need to do this control system. So that's kind of another way to explain why tight ropes, using a pole or pushing your hand up helps you achieve stability. Okay, so the next example, so we did a spinning disc. So let's talk about the spinning disc. So this disc could be a wheel, so a bicycle wheel, or it could be that thing. So let's draw again everything we draw. Nice to draw a picture. So supposing I have some wheel, I'm actually drawing it. So I'm drawing it like this. It's spinning like that. And I'll put an axis in it. So maybe a bicycle wheel, or like that gyroscope that was balanced. And now we'll apply a force on it. I'm going to push the force. So this is going to be some distance r, not the radius of the wheel. It's just the distance from the pivot point. And here's the force F. And the torque is r cross F. So that's this way. So that's the torque. So now, taking the wheel, I'm going to assume that it's spinning, and it has some angular momentum. So there's some subtlety here. When you have a spinning wheel, and you push it this way, it actually turns that. You push it this way, it wants to flip that way. And so this is, anybody who's picked up a bicycle wheel knows a spinning bicycle wheel or a gyroscope, notice this. So it's very counterintuitive, because usually you push things and they move in the direction you push them. But with a spinning wheel, it actually keeps trying to go in the other direction. So the spinning wheel, you look at it and you describe its orientation from the axis position. So this axle. So if it's spinning, angular momentum is aligned with the axis. And so we can think, well, how much if I exert this force for a small length of time? So the torque is perpendicular to the angular momentum if I push it that way. And so remember L is I omega, but omega is a vector that has the length of the angular rotation rate and it's aligned on the rotation axis. So the torque is r cross F. If F is perpendicular to r, and r cross F is perpendicular to r, is perpendicular to L. And so that means the torque, which is the change in angular momentum, is also perpendicular to L. And what that means is you actually have to change the vector direction, not the vector length. So L direction changes. Not length. And so if I change the length, I'm changing. So omega is some length times the direction. If I exert the torque in the same direction as the angular momentum, then I change the spin rate. If I exert the torque perpendicular to it, then I change the direction, not the length. Okay, so let's apply this force for a time delta t. So let me draw this. So delta t is going to, so remember torque is dl dt, is delta L over delta T. So delta L is torque times delta T. So delta L is torque times delta T. So so that's pretty much what I wanted to do, right? And that's equal to R delta T. So the length of L is not changing, the direction of L is changing. So I can draw the new L over here. New L. And this is the change in the angle of the rotation axis. Because remember, L is aligned with the axis of rotation. So how do I, what's an expression for delta phi? It's just this length divided by the L is delta L over L. So let's write down what that is. R F delta T over L, which is I omega. So, and I could move this delta T to the other side and talk about phi dot if you wanted to, but this pretty much tells you what you want to know. So if omega is big, so if the spin is fast, then the change in the angle of the axis is really small. So if I have a wheel and I spin it really fast, I exert a force on it, it's not going to change angle very much at all, if it's spinning really fast. If it's not spinning much, then I'll be able to really turn it. It'll turn in the opposite direction that you expect, but it'll turn. So this kind of shows you what happens. Delta phi is small if omega is big. And that's why rapidly spinning things are stable. Delta phi is also small if I is big. And so if you look at how gyroscopes are designed, they, so here, this one is an example of a gyroscope. It's really heavy, and it's also got most of the mass in the rim, so not much mass. You can see how it's designed here. It's got this huge brass rim to it, so a lot of mass is in the rim that increases the moment of inertia. So rapidly spinning things with big moments of inertia are hard to turn, and that's why gyroscopes and wheels are used for stability. So gyroscopes are used not just, to keep track of direction on spacecraft, they actually also stabilize the spacecraft. And they're used for those, those scooter things that people go around, and there's gyroscopes in them too to try and help you stand up. So, lots of practical applications for gyroscopes. Yeah, so that pretty much shows that. So do we have any questions? Since we're going to start either more demonstrations or more examples. Questions, anybody? Yes?
Yeah, so could you go over why is torque in the opposite, like a different direction of force? Is that just because it's a cross product?
Yes.
Okay.
Right, exactly. So remember, torque is R cross F. And in this particular example, it's a spinning wheel, and I'm letting it spin, and then I'm pushing it that way. So I'm exerting a force up, and it's going to turn. Delta phi is going to be in this direction, which is why it's counterintuitive for a spinning thing. Yes, that's why. More questions? It's a little bit subtle, you know, you think of like, yeah, it's spinning, that's why it's stable, but it actually has to do with the time scales involved with changing direction. And the tightrope problem is, you know, it's actually a tightrope. I was like, oh, I want to do a bicycle example, so I started looking at stability of bicycles, and that is a really, it involves like what the angle of the handlebars are and what the angle of the front fork is with respect to the direction of the handle. So the stability of a bicycle is like a whole field in itself. But why it is that you can, you know, if you have a bicycle, depends on how the handlebars and the angle of the fork is, whether you can easily balance without, you know, ride a bike without your hands on the handlebars. So if you change, actually, I have my bicycle now, I shifted the handlebars, and now it's really hard to balance without hands, but I used to be able to. So I've changed it, made it a lot harder to balance, but actually you can. So, but that's a much more detailed calculation. I was kind of hoping to put it in. I was like, wait, this will take like 10 pages to discuss properly. But if you're interested, take a look. The wiki article is pretty long. It's actually extremely long. Okay, so I guess since we've got these demos up, let's switch. And we only have like a few minutes left of the lecture. Let's play around with some more demos. Yeah. Okay, so let's do this one. So this is just a bicycle wheel, but it's going to show the same stability argument. But I have to spin it up. What I'm going to do is put it up here and let it spin around. Hopefully it won't fly off. Another example of kind of like how you can stay pretty stable. Ordinarily, you just fall right down, but because I put enough spin on it, it was able to keep upright. And then it actually persists. So precession, talk a little bit more about precession. So what's going on? So with precession, so with this thing like this, the center mass is here. So mg is down if it's perfectly horizontal, but if it's not perfectly horizontal, mg is at a slight angle. And so that means the torque will cause the spin axis to change. So if it is very slightly off, then it slowly causes the spin axis to change, and that's what we call precession. So this thing started spinning around. That's kind of what was going on with it. So here's another example. So let's do this one. So it's kind of cute. All these old gyroscopes. Yet another gyroscope, but it's balanced. Actually, so it's designed so that you can balance it. And actually you can adjust the balance right to be exactly balanced if you want. So there, that's pretty close. So, but now I'm going to spin it, and then if I move this, that'll adjust how far off the center mass is from this pivot point. And so this whole thing will will be affected by gravity, and that's going to cause it to precess. And I should be able to adjust the precession rate by adjusting how far off the center mass is. So let's see if we can do that. Yeah, you can adjust the center, you adjust how far off the center mass is, and then it adjusts the precession rate. If I put it on the opposite side, it goes in the opposite direction. And so if I put it so that it would have tilted this way instead of that way, then it's moving in the opposite direction. And as it spins down, remember when we were talking about how faster the angular changes, it depends on 1 over I omega. And so as it spins down, it tends to precess more quickly. And you kind of know that when you put it on a gyroscope, it starts to precess faster and faster as it spins down. And that's what we're seeing here. And I think I can just let this go. I always worry about these things because when they tend to fall over, they tend to jump. And then, you know, they jump in some arbitrary direction. Damn it. So that it doesn't jump out. Okay, so that's basically the demonstration. So the last one is like a wheel where you can hold it up. And I have a gyroscope. Actually, I have a gyroscope at home that I'll try and use maybe next week. One of the cool things you can do with gyroscope is you can say, what if I perturb it at the precession rate? So this is relevant for, say, you know, the Earth is precessing, right? So the Earth is spinning, and because it's misaligned with the sun's torque actually causes the torque from the sun on the Earth actually causes the Earth to spin to precess. Or it's a period. I mean, the moon actually is contributing to this, so you know, to actually compute the rate, the precession rate, you have to take into account all the forces, all the torques on it. But the speed is like, the period is like 25,000 years, and that's why the night sky, you have, if you look at a star on the night sky, you have to specify what's called your epoch. And if I give a position of a star in what's called an RA ascension and declination, which is with respect to the North Pole, I need to specify what year that's with respect to because the North Pole is slowly changing. So, and it's significant enough that if you don't take this into account, when you point a telescope, you're not going to see what you want to see. So you'll be off by arc minutes if you say, use 1950 or instead of 2000 epoch. Or if you don't take into account the current year. So usually when you give coordinates to a telescope, you specify, nowadays usually 2000 epoch, it used to be 1950 epoch. And then it precesses it to the current year so that you get the right position on the sky. So there's a 25,000 year period. But what if you perturb the Earth's orbit with some other, with the same frequency? So like, what if I have a planet going around and it's actually has some orbital perturbation that matches the precession frequency of the Earth? Well, if that happens, you can really change the tilt angle of the Earth. And you can show that with a gyroscope. If you start watching it precess and then you do this at the precession frequency, you can tilt it over. So that's actually gives you ways to tilt planets over. But for a while, I was trying to see if I could figure out a mechanism for tilting Uranus over. I never succeeded with that. But I did manage to find a mechanism that would tilt over all of Pluto and Charon's minor satellites. But it's basically that. You match the precession frequency with some other perturbation of the problem. And in the case of Pluto and Charon's minor satellites, so these are Styx, Kerberos, and Hydra, those are these little moons around Pluto. The perturbation is from Charon, so Pluto and Charon are binary. And if that frequency matches in any way, like some combination of adding it with other frequencies in the system, if any of those match the precession frequency, you can tilt those satellites over. So one of the surprising discoveries from the New Horizons mission was all of them are tilted over in the sense that their spins are in the orbital plane instead of perpendicular to the orbit. Okay, so let's get back here. Whoops, what I like to do, I want to pick a board. Okay, so let's talk about, so we did Kepler's second law. So let's do Kepler's first. We'll start Kepler's first law. Give you only a little bit of time. This is before we start talking about perception. I need to find the chalk. I'll spell my chalk. Okay, so the setting here is not rigid bodies. So we're going to talk about orbital angular momentum. So you can take R cross P for any point mass, and that's, in this case, that's if you use the origin as the sun. So we have the sun here, sun, and we have some planet, and it's in an orbit. I can take R cross P of this thing, and that's the orbital angular momentum. And what we're going to show is the orbital angular momentum gives you the eccentricity of the orbit. So instead of having a circular orbit, we're going to have an eccentric orbit, and so it's going to get closer and farther away from the sun. And the focal point of the ellipse will be at the sun. So I started off by saying this is Kepler's first law. So what's Kepler's first law? And Kepler's first law is the orbit of a planet is an ellipse with the sun at one of the two focal points. So Kepler's first law is the orbit is an ellipse. And the sun is at a focal point. A focal point, that has to do with, how the angles of trajectories off of the focal point. And ellipses in general can be written like this. But in this case, X is from the center of the ellipse, not from the focal point. So we're not going to use that coordinate system to solve the problem, but you can transfer to this. Sometimes people do transfer to this coordinate system to do celestial mechanics problems. Okay, so let's start with energy. So we need to give our mass M, and we need to have an M here. And I'm going to assume that this M of the planet is really small, so that I can have the origin be at the heliocentric coordinate is okay to solve the problem. So energy per unit mass is this. That's correct. So this is energy per unit mass. Oh, there. Oh wait, I'm dividing by M. There we go. That's right. So kinetic energy per unit mass divided by little m. The actual potential energy is d big M little m, and I just re-equal them. So V, I can write as VR squared plus E theta squared. So I'm going to work in polar coordinates. And the origin, so this is from the sun. So the origins down here, and R are radial directions. Radius is this way. V theta hat is in this direction, and R hat's in that direction. So just like we have used polar coordinates before, so we'll write out the velocity like this. Now, angular momentum is R cross P. So angular momentum, R cross MP, actually. So if I write out the velocity in terms of the radial component and tangential component, the radial component goes to 0 because it's parallel to R. And so this is R m d theta, like that. So it's convenient to write d theta squared is equal to L squared over m squared R squared, like that. Okay? And that means I can write the total energy per unit mass. So E over m, L over m, I can write this as 1/2 R dr squared plus L squared over 2 m squared R squared minus G m over R. Like that. So often people use L to be L over m, and they use E to be E over m, because this little m just cancel it out over everything. And so if you're reading any book that talks about celestial mechanics, people will usually refer to angular momentum per unit mass as angular momentum and energy per unit mass as energy. So I want you to notice this equation. So we have an energy equation. It's kinetic energy plus potential energy. So remember, energy is equal to kinetic energy plus potential energy. And our potential energy was this Gm over R. So we drew R, and actually I'm going to put this in the middle. And this is energy. So when we were looking at potential energy curves, this was the potential energy, so it's negative and it goes to infinity. But now we have R dot, that's VR is R dot, and then we have a function of R here, and another function of R. So sometimes people call this an effective potential energy. Minus G over R, let's just put G over R. And what's that look like? Well, it's positive, and if R is big, it goes to plus infinity. So if I draw it, it looks like that. So this is U, which is minus Gm over R. That is U effective. It has this dip in it, and that dip depends on the angular momentum. So where it is, where the bottom is. So if you have less angular momentum, it's slower down. And this is just a function of R. So I can think about how's the orbit in R, the behavior of the orbit in R. So just have like a couple more minutes. So let's draw some pictures. And in fact, I can write an equation of motion that looks like this. With mine. So let's draw again this effective potential. This. Here's my effective potential. Here's 0. That's U effective, and this is R. So if I pick the kinetic energy, but pick the total energy of the orbit now. So let's pick an energy like this. Kinetic energy has to lie in here, but the kinetic energy now is R dot. It's 1/2 mR dot squared. So I'm ignoring the d theta part because I suck that into the angular momentum. Remember, angular momentum is conserved, right? So once I choose L, it's fixed. So an orbit here goes back and forth in this potential well, and but it can vary in radius. So this is actually an elliptical orbit. If I think about what happens at the bottom of the potential well down here, that orbit can't go anywhere. So that's a circular orbit. And what if I have a positive energy? So this is energy 0. So these have negative energies. If I have a positive energy, then I have a minimum radius. That's like a pericenter. This is a hyperbolic orbit. And if I have exactly 0 energy, I can start at some pericenter distance and escape to infinity just barely. Those are the parabolic orbits. So this effective potential, which now takes into account the angular momentum, is a nice way to classify the system once you know the angular momentum. And of course, I can draw this curve again for different angular momentum. So if I had a smaller angular momentum, it would go lower, and the circular orbit would be smaller. And if I had more angular momentum, I could draw it, and the circular orbit would be larger radius. Anyways, we're out of time, so I'll stop there. And what we'll do next time is actually show that we get an elliptical orbit by solving nuclear conversion. What? Oh, yeah.